So today's our topic is alternator on load, operation of alternator on load. Okay, content of today's lecture: introduction about then the effect of load on alternator when load is connected. At that time, what is the effect of load on alternator? Then we'll discuss the phasor diagram of alternator on load. So for different power factor, we'll draw the phasor diagram of alternator. Okay, and then in last we will summarize today's topic. Okay, so whenever the load on alternator is varied, the terminal voltage will also vary. Okay, so we assume that the load is not connected on alternator. Okay, so when load is not connected on alternator, the rotor winding of alternator is open circuited. Okay, and when load is connected to alternator, at that time we can say that rotor winding is closed type. Okay, so when rotor winding, that is the armature winding. Okay, so when armature winding is closed, at that time what happens, current will also flow through the armature winding, and due to this current some voltage drops. Okay, so when load is varied, okay, we can say that we have a different type of load: capacitive load, inductive load, and resistive load. Okay, so when different type of load is connected, at that time there is effect on terminal voltage. So we can say that load is varied, we can say that the terminal voltage will also vary. This variation in terminal voltage is mainly due to the three reasons. Okay, okay, we say that the load is increased or decreased, according to that the terminal voltage will increase or decrease. Okay, but this increment or decrement in terminal voltage depends on these three reasons. Which are these? The first is the voltage drop due to the armature resistance. Okay, when current is flowing through the armature winding, at that time some voltage drop due to the resistance. So first reason is voltage drop due to the armature resistance. Second reason is voltage drop due to the armature leakage reactance. This is the second reason, voltage drop due to the armature leakage reactance. Third reason is the voltage drop due to the armature reaction. That will we already discussed it, armature reaction. Okay, so voltage, third reason is the voltage drop due to the armature reaction. These are the three reasons for variation in terminal voltage. Okay, so first effect of load on alternator, that is the voltage drop due to the armature resistance. Okay, we knew that in rotor winding or in armature we have a armature winding. Okay, and this armature winding has some resistance. Okay, we assume that this armature winding has Ra resistance, that is denoted by Ra. Okay, so when load is connected, at that time current is flowing through the armature winding which has Ra resistance. Okay, and in electrical we knew that when current is flowing through any conductor or winding which has some resistance, at that time some voltage drops in that winding. Okay, so here what happens, the current is flowing through the armature winding which has Ra resistance, so IRA drop. This voltage drop is known as the IRA drop or IARA drop. Okay, so this IARA voltage drop occurs in this armature winding, and the voltage drop due to this resistance. So whatever voltage drop occurs in this armature winding, this armature winding resistance voltage drop is in phase with the armature current IA or I. Okay, so here we have a voltage drop, that is the IARA or IRA voltage drop. This IARA voltage drop is always in phase with the armature current. That means there is no angle between armature current and IRA voltage drop. Okay, this is the voltage drop due to the armature resistance. Now next effect is the voltage drop due to the armature leakage reactance. So when current flows through the armature conductors, what happens? The flux will start to flow through the armature core. Okay, As soon as the current flows through the armature winding or armature conductor, what happens? Flux will set up, and this flux will start to flow through the armature core. Among these, whatever the flux produced by this armature conductor or armature winding, some of this flux will take a different part, okay, and do not cross the air gap. This type of flux is known as the leakage flux. Okay, from 100% of flux, some 10% or 15% flux will take some different part. Okay, and this flux is known as the leakage flux. So look at this image. Okay, so these are the stator conductors and these are the rotor conductor. Okay, so in between this, some flux will take some different part. Okay, so this flux is known as the leakage flux. Okay, and this leakage flux depends on the current flowing through the conductor, armature conductor. Okay, so if the value of current increases, the leakage flux increases. If the value of current decreases, the leakage flux will decrease. Okay, so whatever amount of this leakage flux, that depends on the magnitude of current that is flowing through the armature conductor. Okay, and this leakage flux has some relationship with the terminal voltage. Okay, so now whatever leakage flux is there, this leakage flux will set up an EMF because of self inductance. This leakage flux will do the EMF generation. Okay, or it generates the EMF. This leakage flux will generate the EMF. Why the EMF is generated? Because this leakage flux has some self inductance. So due to this self inductance, the leakage flux will set up the EMF. Now whatever the EMF is generated, this EMF is known as the reactance EMF. Why it is known as the reactance EMF? Because it is generated by the leakage reactance. Okay, so whatever EMF generated by the leakage reactance, that is known as the reactance EMF. Okay, and this reactance EMF leads the armature current I by 90 degree. Okay, so first we have armature resistance drop, IARA drop. It is always in phase with the armature current. Now second voltage drop is due to the armature leakage reactance, and this armature leakage reactance drop, or we can say that a reactance EMF, it leads the armature current I by 90 degree. Okay, so the armature winding is said to process a leakage reactance. Okay, if the EMF is generated due to the self inductance, so we can say that this armature winding possesses a leakage reactance and the voltage drop. So current is always flowing through this armature winding which has the leakage reactance Ixl. So we can say that the voltage drop due to this reactance is Ixl. Okay, and the generated EMF has to overcome the voltage drop due to the leakage reactance to give its output. So second voltage drop is the Ixl drop or Ixl drop. Okay, voltage drop due to the armature leakage reactance. Okay, and it always leads the armature current by 90 degree. Now next is the voltage drop due to the armature reaction. Okay, so armature reaction is the effect of armature flux on main field flux. We already discussed it, armature reaction. This effect of armature reaction can be seen in DC generator also. Okay, armature reaction occurs in the AC generator, that is the alternator, as well as the DC generator. Okay, but compared to the DC generator, what happens? The power factor of the load in an alternator has a considerable effect of armature reaction. Okay, in DC generator there is no effect of load, of power factor load. Okay, but in AC generator the effect of armature reaction has a considerable effect due to the load on alternator. Okay, so While we talk about the power factor on loading conditions, we consider the three cases, that the unity power factor load, zero lagging power factor load, and zero leading power factor load. Okay, so voltage drop due to the armature reaction may be assumed as there is a presence of fictitious reactance XA called the armature reaction. Okay, armature reaction occurs, okay, in armature winding alternator. So we can say that this armature has some reactance. Okay, so when armature reaction process is there, at that time some reactance comes into picture, and this reactance is called the armature reactance. Okay, and that is denoted by XA. Okay, so when current flows through the armature winding, at that time some voltage drops or some voltage drop occurs in the armature or alternator due to the armature reaction, and that is represented by IAXA. Okay, so when armature reaction is there, at that time some voltage drop occurs, and this voltage drop is known as the voltage drop due to the armature reaction, and it is denoted by IXA or IAXA. Okay, understood. So we have a three effect: voltage drop due to the armature resistance, that is IRA drop; voltage drop due to the armature leakage reactance, Ixl drop; and third drop is the voltage drop due to the armature reaction, that is the Ixa drop. Okay, understood. Now next is the synchronous reactance and impedance. So the leakage reactance Xl and armature reaction reactance XA together called as the synchronous reactance. Okay, if we combine these two, leakage reactance XL and armature reaction reactance XA, so if we combine these two, then it is combinedly known as a synchronous reactance XS. So XS, synchronous reactance XS, is equal to XL plus XA. Mathematical formula is XS is equal to XL plus XA. Okay, now if we combine these three voltage drops, armature resistance voltage drop, leakage reactance voltage drop, and armature reaction reactance voltage drop, then we can write that V is equal to voltage drop due to the armature resistance plus J into IXL, that is the IXL is the voltage drop due to the leakage reactance, plus J into Ix, that is the voltage drop due to the armature reaction reactance. Okay, so this is the formula, that V is equal to IRA plus J IXL plus J IXA. Okay, in this formula, if we take current, armature current I as common, then equation becomes V is equal to I into RA plus JXL plus JXA. Okay, so further simplification of equation, V is equal to I into bracket RA plus, now we are taking J as a common. Okay, so plus J into XL plus XA. Now what is this XL plus XA? This XL plus XA is the synchronous reactance axis. Okay, so equation becomes V is equal to I into RA plus JXS. Okay, and this equation is further written as V is equal to I into ZS, where ZS is known as the synchronous impedance of an alternator. Okay, so if we combine the armature resistance and a synchronous reactance, so by combining armature resistance and synchronous reactance, the synchronous impedance is made. Okay, so synchronous impedance is the combination of armature resistance and a synchronous reactance. Okay, and mathematically we can write it ZS is equal to under root RA square plus XS square. Okay, ZS synchronous impedance ZS is equal to under root RA square plus XS square. Okay, so formula V is equal to IZS, where ZS is the synchronous impedance. Okay, from the above discussion, it is clear that the variation in load causes the terminal voltage of alternator to change. Okay, due to these effects, what happens, whether the terminal voltage will increase or terminal voltage will decrease. it is due to the synchronous impedance of the alternator. Finally, we can say that whatever change in terminal voltage occurs, this change is due to the synchronous impedance, and this synchronous impedance is the combination of armature resistance and synchronous reactance. Okay, so finally we can say that terminal voltage will increase or decrease, that will depend on synchronous impedance also. Okay, now next is the phasor diagram of alternator on load. Okay, so to draw the phasor diagram, we should know the various terms used in this diagram. Okay, so first term is the E0. Now what is E0? E0 is the no load voltage, no load terminal voltage. It is the maximum voltage induced in the armature without giving any load. Okay, 0 stands for no load. Okay, so E0 is the maximum terminal voltage without load or in no load condition. Next is the capital E. Capital is the on load terminal voltage. That means it is the terminal voltage when load is connected. Okay, next is the capital I or IA. That is the armature current per phase, current flowing through the armature winding. Next is the capital V. It is the terminal voltage. It is vectorially less than the E by IZ and also vectorially less than E0. Okay. Next term, that is the phi. That is the cosine of angle between terminal voltage and current. Okay. These are the terms used in the phasor diagram. Okay, now next is the phasor diagram for unity power factor load. Okay, we assume that the load connected to alternator that is of unity power factor type. Okay, so the procedure, how can we draw the phasor diagram for unity power factor load? Okay, so first of all, what we have to do, we have to take voltage phasor V as a reference phasor. Okay, look at this phasor diagram. Okay, here this OA is the voltage phasor that is taken as a reference phasor. Okay, O and A, this phasor is the reference phasor. So voltage phasor is taken as a reference phasor. Okay, now we assume that the power factor is the unity power factor. Okay, so in unity power factor, the voltage and current both are in phase. That means the angle between voltage and current is 0. Okay, so draw the current phasor in the same line of voltage phasor. Okay, so this is the current phasor. Okay, and this voltage phasor and current phasor both are in phase. So for our understanding, we can say that both are in the same line. Okay, now next is the armature resistance drop, phasor of armature resistance drop, IARA. Okay, now this armature resistance drop, IARA, is always in phase with armature current. Okay, that means the angle between IARA drop and armature current is 0. Okay, and from the extremity of the V phasor. Okay, so we can say that at the end of voltage phasor, this point is the end point of voltage phasor. Okay, so we have to add this IARA drop, armature ohmic drop, IARA drop at this end. Okay, and it is always in phase with the armature current. Okay, so here the angle between armature current and IARA drop is 0. Okay, and it is added at the end point of the voltage phasor. So this is the AB, this is the A point, this is the B point, this is the IARA phasor. Okay, now next is the armature leakage reactance drop, that is Ixl drop. Okay, and this Ixl drop is always drawn perpendicular to the current phasor. Okay, so we have to draw the this is the Ixl drop, and it is always drawn perpendicular to the armature ohmic drop. This is the end point of IARA drop, and we have to add at this point to the Ixl drop. perpendicularly. Okay, so this is the armature leakage reactance drop. Now next is the armature reaction drop. So this armature reaction drop is also drawn perpendicular to the armature ohmic drop. Okay, and it is added at the end point of the armature reactance drop. So this is the end point of armature leakage reactance drop. Okay, so we have to add this IAXL phasor at this point perpendicular to the IARA drop. Okay, so now connect this point and O point. Okay, so if we connect O point and this point, that gives the E0, that is the no load induced EMF, that is load is not connected. Okay, that is E0. Now connect O point and this point, it will give the on load induced EMF, on load induced EMF, that is E. Here it is E0, here it is E. Okay, and if we combine these two, IAXA and IAXL, then it is the IAXS drop. Okay, so this is the phasor diagram for unity power factor load. Okay, now next the phasor diagram for lagging power factor load. Okay, so lagging power factor load, that means current lags behind the voltage by phi angle. Okay, so first step is we have to take voltage phasor as a reference phasor. Okay, so this is the voltage phasor V. So this O and A is the voltage phasor, and we are taking this voltage phasor as a reference phasor. Okay, now next we have to draw the current phasor, and we are drawing this phasor diagram for lagging power factor. Lagging power factor, that means current lags behind the voltage by phi angle. Okay, so this is the current phasor, it lags behind the voltage phasor by phi angle. Okay, this is the current phasor. Okay, so two steps are completed. First we have to draw the voltage phasor as a reference phasor, and then we have to draw the current phasor which lags behind the voltage phasor. Okay, now next is the armature ohmic drop, that is the IARA drop. Okay, this IARA drop, is always in phase with the armature current. Okay, that means the angle between this armature current and IARA drop is 0, or we have to draw this IARA drop in the same direction of the armature current. Okay, this is the direction of armature current, so we have to draw this IARA drop in the same direction of armature current. Okay, this is the end of voltage phasor, so we have to add this IARA drop in at the end of this voltage phasor in the direction of the armature current. So this is the IARA drop, armature ohmic drop. Now next drop is the IAXL drop. Okay, IAXL drop is we have to draw this IAXL drop perpendicular to the armature current at the end of the armature ohmic drop phasor. Okay, so we have to add this IAXL drop at the end of the armature ohmic phasor perpendicularly. Okay, now next is the armature reaction drop, IAXL drop, that is added into IAXL drop. Okay, so now we got this point, connect this point and O point, which gives the no load induced EMF is 0. This connect this point and O point, which will give the on load induced EMF. Okay, if we combine these two drop, then it will give the IA access drop. So this is the phasor diagram for lagging power factor load. Now next is the phasor diagram for leading power factor load. Okay, leading power factor, that means current leads the voltage. Okay, so here we are taking voltage phasor as a reference phasor V. Now current leads this voltage phasor by phi angle, so here is the current phasor. Okay, this is the current phasor and it leads the voltage phasor by phi angle. Now we have to add this IARA drop into voltage phasor at this point. Okay, and in the direction of armature current. Okay, so direction of this IRA drop and direction of this armature current both are same, and it is added into the voltage phasor. So this is the armature ohmic drop phasor. Now in this armature ohmic drop we have to add this Ixl drop perpendicularly. Okay, so this is the perpendicularly we have drawn this Ixl drop into this IARA drop. Okay, and in Ixl drop we have to add the Ixl drop. Okay, and combinedly it is known as the Ixl drop. Okay, now connect this point and this point, that is the no load induced EMF. Connect this point and this point, that is the on load induced EMF. If we connect these 2 points, then it will give the IAZ drop. Okay, and if you connect these 2 points, then it will give the IAZS drop. So this is the phasor diagram for leading power factor load. Okay, so today we discussed about effect of load, different type of load on power factor. When load is of resistive type or inductive type or capacitive type, at that time what is the effect of load on alternator, then what is synchronous reactance and synchronous impedance, and how can we draw the phasor diagram for unity power factor, lagging power factor and leading power factor load. What is the procedure of the phasor diagram of alternator? Okay,